Chemistry. We're on to our last lesson of the electrochemistry unit, and this is on two different topics. It's the Nernst equation and balancing redox reactions. So the Nernst equation allows for the calculation of EMF voltage at non-standard conditions. So remember when we calculated the voltage for the copper, a zinc copper cell, it was at standard conditions. That means 1 molar, 25 degrees. What if the conditions are not standard? Then this equation allows you to make that calculation. So here's the Nernst equation. So it says that the potential of a cell is equal to the standard potential, and again, that's a number that you can look up for two different elements, so it's not something you have to figure out, minus the gas constant times the temperature over the number of moles over Faraday's constant times the natural log of Q. So let's define what all those terms mean. So E is the EMF at non-standard conditions. That's what you're trying to find. E standard is the standard EMF, and we've talked about that earlier. R is the gas constant. Now the one you want to use is 8.31 joules per mole Kelvin, not the one that we use in PV equals nRT. F is Faraday's constant. We saw that earlier. N is the number of moles of electrons transferred. So in the case of the copper zinc reaction, it was 2 electrons or 2 moles of electrons. So example, we will examine the zinc copper cell under non-standard conditions. So going back to the equilibrium unit, the value of the reaction quotient Q is calculated the same way as the law of mass action. In other words, products over reactants. For the zinc and copper cell, that can be expressed as, so there's the reaction in its net form. So you have copper 2 plus ions and zinc atoms in solid, and what happens is the copper is reduced and becomes a copper atom. That's a solid in the copper strip, and the zinc ionizes to become zinc 2 plus ions, and those are the ones that went in solution. So when you write the law of mass action, remember that you don't use the solids, you only use the aqueous. So the law of mass action equilibrium is as follows. Remember, do not include the solids. So it's simply going to be Q equals the zinc on the product side over the copper on the reactant side. So what is the EMF for the following zinc copper reaction? So we're going to use non-standard concentrations. Remember, standard concentration is 1 molar. We're going to use 5 molar for the copper and 0.5 molar for the zinc. So we're going to use more than standard for the copper and less than standard for the zinc. So that means the Q would be the products over the reactants, which would be 0.05 over 5 for the Q value. Again, Q is just like equilibrium constant, except at non-standard conditions. These are non-standard concentrations, so we use the Nernst equation. So there is the Faraday's constant. Now we're going to say temperature is 300 K. Standard temperature would be 298. We could have used any non-standard temperature here. N is the number of moles, so that's 2 electrons in the zinc copper example. R is the 8.31, not the 0.0821 that we use with PV equals nRT. And the E standard for a copper zinc cell we've already found is 1.1 volts. Okay, so now we're going to plug that data into the Nernst equation. So there's the Nernst equation again. And this produces the following. R is 8.31. T is 300. I'm excluding units of measure, just we're going to ignore those here. Down at the bottom, the number of moles is 2 moles of electrons. Then you have Faraday's constant, and then you have Q, which is the natural log of Q, which is 0.05 over 5. And then the standard potential is the 1.10 that we learned in the previous lesson. And when you plug all those numbers in, crunch all those numbers, you get that the potential in those conditions, those concentrations and temperatures, will be 1.16 volts. So explanation, since we have a high concentration of copper ions to gain electrons, that is to be reduced, so more voltage is produced than the standard of the 1.1 that we got at standard conditions. A quick mention of something called electrolytic cells. Everything we've been talking about are voltaic or galvanic cells. They produce electricity. An electrolytic cell is a backwards battery. It produces a non-spontaneous reaction that requires energy input to do some work. So you have to put electricity into an electrolytic cell. So why would you want to do that? Well, you've probably heard of the process of electrolysis. So an example of electrolysis is plating silverware, which is not really silver, but it produces a shiny surface. So electrolysis is used for a lot of industrial processes. So you put energy in, and it basically runs the battery reaction backwards, and that's what an electrolytic cell is. Okay, now we're going to move on to a different topic, and this is balancing redox reactions in acidic solution. I'm just going to touch on this. This is going to seem a little confusing at first, but if you practice about 3 or 4 of these, they will make sense. So what you have to do in a redox reaction is not only balance the atoms, number of atoms like we've traditionally done in a chemical reaction. You have to have the same number of hydrogens on the left as on the right, same number of oxygens left and right. But you also have to balance charge here, and it makes it a bit more complicated. So balancing redox reactions requires both mass, that's the number of atoms of each element, and charge be balanced. The method used for balancing redox reactions is called the half reaction method, and I like to call it the OOHE method. So it's OOHE minus. So we'll see what those stand for. So divide the chemical reaction into 2 half reactions, an oxidation reaction and a reduction reaction. Balance the other elements except for oxygen and hydrogen. 3. Balance oxygen by adding water to each side as needed. Balance the hydrogen by adding hydronium ions as needed. This is true for an acidic solution. If it's a basic solution, you add OH minus. We're not going to do that here. 5. Balance the charge. That's the electrons. So you see the OOHE. It's OOHE. So that's the mnemonic to remember this. Then you multiply each half reaction so that the charges E minus cancel out. And then you add the half reactions. And then you check to make sure your charges are balanced. You're done with the balancing. Okay, so we're going to balance the following reaction. Now note that this is an incomplete reaction called a skeletal reaction, but that does not affect the balancing. So I got this example out of your textbook in the electrochemistry chapter, so I'm simply following that. So don't worry that it's not a complete reaction. We're going to make it a complete reaction by doing this balancing process. So divide the chemical equation into 2 half reactions, an oxidation reaction and a reduction reaction. Okay, chromium is the reduction reaction. We've already seen this ion before, the dichromate ion, and the chromium is a 6+ or a +6. Okay, we've seen that in an earlier lesson. So it's going from a +6 to a +3, and that means it's a reduction. The chlorine is an oxidation. That means it's going to increase its oxidation number. It goes from -1 on the left side to 0. A Cl molecule, chlorine molecule, is a 0 charge, so it goes from -1 to 0. That's an oxidation. It's increasing its oxidation number. Follow the balancing process for each half reaction separately. So we're going to start with the chromium. So balance the chromium half reaction. So balance other elements except oxygen and hydrogen. So first we're going to balance the chromium. So there it is. You see that the chromium is now in balance. We put a 2 on the right side to balance the 2 CRs on the left. Now you're going to balance oxygen by adding H2O to each side as needed. So if you look over on the left side, you see 7 oxygens. So how many H2Os are you going to have to add to the right side so that you have 7 oxygens? So balance the oxygens. You add 7 waters to the right side. I know this seems odd, but it is just a standard way of balancing these reactions that you're supposed to know. So in other words, if you look at the left side, there's 7 oxygens. If you look over on the right side, there's now 7 oxygens. Balance the hydrogens by adding H+, hydronium ions as needed. Now in this case you add H+, don't add H3O+, just add H+. So let's look at hydrogens in step 3. You have 14 in all. 7 times H2 is 14. That means you're going to have to add 14 to the left side. So since this is an acid reaction, balance the H using hydronium ions, and there you see that that's done. You added 14 hydronium to the left side to balance the 14 hydrogens over on the right side. So now oxygen and hydrogens are balanced. Step 5, balance the charge. Okay, so you're going to have to do some counting here. So if we look over on the left side, we have 14 positive charges with the hydroniums, and then we have a 2 minus on the dichromate ions. So 14 minus 2 is a positive 12 charge on the left. If we go over on the right, we have 2 times 3 plus for the chromium. That's 6 plus. The water doesn't have any charge on it. So we have 12 plus over on the left and 6 plus on the right. So we need to make those equal. So how do you do that? And remember, electrons are negative. So if you add 6 negative signs to the 12, you'll get 6. You'll get positive 6. So let's see that happen. So there we go. So it's 14H plus and 2 on the dichromate ion gives you a plus 12 on the left. You have 2 times 3 plus on the right is a plus 6. So you need to get from 12 down to 6. So you have to subtract 6. And remember, electrons are negative. So what you're going to do is add 6 electrons to the left side. And there we go. So now you have the charges in balance. So now everything's in balance. Chromium, oxygen, hydrogen, and the charges. Compute the total charge on each side and add the electrons to the more positive side so that the charge is balanced. Now we're going to balance the chloride half of the reaction. This is a little simpler. So balance other elements except oxygen and hydrogen. So the only thing we have is the chlorine. So we have 2Cl on the left to balance with the Cl2 on the right. So you balance the chlorine. Now you balance the oxygen by adding H2O to each side, but there's no oxygen. So you don't need to do that. Skip this since there are no oxygen to balance. Now you balance the hydrogen by adding hydronium ions as needed, but there's no hydrogens, so skip this. There's no H to balance. Now you balance the charges. So there we are. So you have a 2 minus on the left and a 0 charge on the right. So you're going to add electrons to do that. So you're going to add 2 electrons to the right. So you're going to take the 0 minus 2 is going to give you 2 minus. So that's how you balance that. So that's a -2. That's a 0. So now we're going to add 2 electrons to the right side. So now the charges are in balance. So now you have everything in balance. So now we're going to put both equations together. So you multiply each half reaction so that the charges E cancel out. Okay, so there, now you had 6 electrons in the chromium half of the reaction. You remember that from a few slides back. Now you need 6 negative charges on this reaction so that the -6's on both sides cancel. So now you have excuse me. So there is the chromium half of the reaction, and there's the 6 electrons we talked about over there on the left. So now we put both of them equations together. So there is that. 3 times 2e minus is 6. So multiply this reaction by 3 to get 6 electrons. And there you have the 6 electrons in the chromium reaction. So that means the chloride reaction is going to give you 6 electrons on the right. So now you've balanced the electrons for each of the 2 reactions. But you had to go ahead and multiply everything else in that reaction, the first one up above, you had to multiply everything by 3. So now it's 6Cl minus produces 3Cl2 plus 6 electrons. Okay, and there's the chromium reaction. So now we're going to put those 2 reactions together. So first we're going to cancel the electrons. They cancel on both sides. And now we're simply going to add the reactions like we would in Hess's law. So now you have 14H plus on the left plus the dichromate plus the 6 Cl minus. Then over on the right, you have the 2 chromium ions, you have the 7 water molecules, and you have the 3 chlorine molecules. So check to make sure the charges are balanced. So we have plus 14 on the left, minus 2, which is 12, minus 6, the 6 Cl minus. That gets you to positive 6. Over on the right, we have 2 times 3 is positive 6, and the water and the chlorine molecule have no charge, so you have plus 6 on both sides, so the charges are balanced. So this is the final balanced equation. The equation is balanced for both charge and number of atoms. All right, and that takes care of our final lesson in electrochemistry. All I'm going to have you do is practice that reaction 3 times to be sure that you can do it. By the 3rd time, you should be able to do it by memory. All right, and that takes care of this lesson.